Hello everyone, welcome to today's talk on building a custom LSTM cell in Pytorch and thereby opening the magic LSTM black box. So in this talk, basically I'll be focusing on and walking you through the LSTM cell architecture and then implementing it from scratch in Pytorch. Then moving forward, I'd like to introduce myself. My name is Shreya Sajal and I am a pre-final year student at IIT Guwahati. Currently, I am a Kaggle Notebooks Master, ranked at around 200 and a 2 into expert in the discussions and dataset section on Kaggle. And then, other than that, I was recently offered the Applied Scientist intern role at Amazon for the summer of 2022. So, moving forward, I would like to uh, give the required credits for the content of this talk. So, there is this AI Summer blog. They curate very good blog posts, and their understanding LSTM blog post was very helpful. And this entire presentation is the content is influenced by their blog post, and then this GitHub repo of this ML scientist Piero Esposito that I've mentioned the links in my slide. So moving forward to what's in store for today's talk. So first I'll be covering some RNN basics because LSTM is one of the most interesting architectures of the recurrent neural networks. So before directly jumping to the LSTM architecture, it can be very overwhelming at first, but then if I just cover the some of the basics of the RNN, then move to the LSTM architecture, and then the equations and the gates, that's the maths or what is happening behind the hood, that maths will help you understand that. And then I'll move to the Pytorch Scratch implementation. So once the maths or the equations and the gates are clear, then the Pytorch implementation is just a cakewalk. So I'll move forward. So a quick glimpse into a simple RNN cell. So as you can see in the figure, it is basically a common neural network with shared weights. The weights are same for every time step and it is taking in sequential data. So, and that sequential data can be of variable length. So that is a limitation when it comes to a common neural network. You cannot pass in variable length data, but then RNNs were able to overcome that limitation. One can achieve this by connecting the time steps output to the input. So this is called the sequence unrolling. The entire sequence is unrolled into the different time steps and then the processing of the whole sequence is done, and we have an algorithm that takes into account the previous states of the sequence as well. So in this manner we are having a notion of memory in a cell. So this is what so this is the simple RNN cell. Now moving forward, so what is back propagation through time? So this is basically a method that is used for learning of weights in a recurrent neural network. So one thing that we talked about in the last slide was that the RNN networks have this feature of input unrolling, which means that when it is provided with a sequence of length n, it does not process the entire sequence at once, rather it processes the input into time steps and then it processes each time step. So when we talk about the learning of the parameters, the weights of this in this recurrent neural network, so how does this take place? So it basically takes place through back propagation through time. So back propagation through time, it is based on the unrolled input. So we can calculate a different loss per time step, and then that loss is back propagated, and the error of the multiple losses uh, to the memory cells is like back propagated, and in this direction we can compute the gradients from the multiple paths, and then these are added to calculate the final gradients. So this is how the back propagation through time works. So moving forward, we now come to the LSTM. So that is long short term memory cells. So the LSTM is one of the most interesting architectures and the recurrent neural networks. It enables to the model to learn from long sequences, but it also creates a numerical abstraction for the long and short-term memories, being able to substitute one for another whenever needed. So there was this problem in recurrent neural networks that was of the vanishing gradients or exploding gradients. So l- the long-term dependencies were not being captured by the recurrent neural networks. So when LSTMs were introduced, they were able to overcome this limitation of recurrent neural networks because they had a gated structure. So this gated structure enabled them to take in account the long and the short term memories. So they have some mathematical operations that make the information flow, this entire gated structure. And because of that, it is able to decide between its long and short term memory and output reliable predictions on the sequence data. So this is gist of the LSTM. Now we'll be moving part by part in this long short term memory cells and we look into the architecture. So uh, this is a picture that you'll be basically finding mostly in on the internet whenever you type LSTM architecture. So you can be overwhelmed at first looking at this, like what is this? There is so much to it. But then I hope that in the following slides I'm able to make you understand what actually is this entire working by taking in the equations step by step and how it works. So, some important points before moving further into the maths is that all the equations that I'll be mentioning further, the weight matrices are indexed. So, you will see something like I, X, or FIT, something like that. So, that is basically the first index is the vector that they are processing, while the second index refers to the representation, that is the input gate or the forget gate. So second representation refers to what you are mm, turning after the processing, turning it into. If you are calculating for the input vector, then input gate vector, then it is W X I. If you are taking in the input that is X and you are processing it and making it into I, so it is WXI. So you will understand it when you move further. Then dot with the outer circle represents element-wise multiplication, that is the Hadamard product basically, and the matrices are depicted with the capital bold letters, while vectors with the non-capital bold letters, that is the standard notation. So moving further, we have the equations of the LSTM cells as it is mentioned over here. So here the xt that is there is basically a vector of n dimension, and here n refers to the feature length of each time step. So I can make you understand like what is the feature length at each time step means. At each time step means. So for example, if you're taking a sentence, say it is having 5 words. So for every sentence, you are having an embedding, because you know machine learning models, any type of model, they work with numbers. You cannot pass text directly, so you have embeddings for that, feature embeddings. So for example, I take word to vector or glove embeddings, say they are 50 dimensional. So that 50 dimension, that is the feature length of each word. So each word will have an embedding of 50 dimension. So that is the feature length n, that is what it refers to over here, xt. And then the other things that are there, it, ft, ot, ht minus 1, ctt. So the t thing is basically the time step, whereas these are in the h dimension, and it is the hidden state dimension. Hidden state dimension, that is the uh, number of neurons in the hidden state, because you can see just that hidden state, but inside that there are many neurons, right? So that hidden state dimension is basically the dimension of the vectors, like the input gate vector or the forget gate vector or the output gate vector or the hidden state vectors and or the cell state vectors that we will be looking forward. And these are the 5 main equations of the LSTM. You can see as we talked about the capital W bold XI. So it is taking in X, like you are seeing that this is having the product with this matrix multiplication with X T, and it is giving I. So therefore therefore it is having that index XI. So that is easy to understand. So I'll move further. So the first equation is of the input gate. So the input gate, as you can see, it is obtained after applying this sigmoid activation over this linear combination that you can see here. There is this weight matrix and there is this matrix multiplication with the xt, that is the input at the current time step. Then you have ht minus 1, with which there is this another weight matrix, a product with the ht minus 1, and there is this third weight matrix that is calculating the product with ct minus 1. So ht minus 1 is the previous hidden state uh, vector, and ct minus 1 is the previous cell vector, that is the context vector. So when we look at the dimensions, so the dimension of H and C is same, that is batch size into the hidden state dimension, whereas the hidden state dimension is basically a parameter of the hidden state, and it is like the neurons. But that term is now depreciated, and the term that is mainly used is the hidden state dimension or the number of neurons in the hidden state. And then we have xt, that is the current time step input, that is having the batch size into feature length dimension. So feature length here refers to, as we talked about, say the dimension of the embeddings that you're using. For example, if you're using a 50 dimensional word embedding, then the feature length is 50. So basically this was about the input gate. We'll later see how the input gate is actually acting as a filter for the input that is passed, that is used for generating the new cell state vector. So equation 2, we saw the forget gate. The equation is almost the same as the equation above that you saw for the input gate, but here we are modeling something different and the weight matrices have a different meaning. But then it is also taking the current input, current time step input, and the previous time step hidden state and the previous time step cell vector. So that is something that is same. Then we have equation 3, that is the new cell or context vector. So here you can see that we have already learned a representation that corresponds to the forget as well as for modeling the input vector. There were f and I that we saw in equations 1 and 2. So we can keep them aside and then we inspect the tanh activated uh, function over here, the tanh activation that is applied, this entire term tanh, and there is this linear combination of this matrix multiplication, and then there is this bias term that is just a vector that is added. So that's not something very complex. It's also a learnable parameter, like the weight matrices. So here we have another linear combination of the input and the hidden vector, which is again totally different. And this term is the new cell information that you see in the that is passed to the tanh activation function in the rightmost part of this equation for the new cell state. So this is the current cell information. So it is basically passed to the tanh function to introduce non-linearity and to stabilize the training. But we don't want to simply update the cell with the new states, that is the new cell information. Therefore, we see such a big equation, or it would just have been a tanh activation function. But then this would defeat the entire purpose of the LSTM cell, because you see it is having the long short-term memory and it is having the mathematical abstraction for both the long and the short-term memory. So here you have there comes the role of the input and the forget gates that we just mentioned in the previous slide. So the input gate actually acts as a filter to the new cell information, that how much of it has to be passed, because the input gate was a value between 0 and 1 and it decides that how much of the cell information has to be passed. And similarly the forget gate also was a value between 0 and 1 because there was a sigmoid activation function used. So it also decides how much of the previous cell state information, because you see in the forget gate, it is having this element wise multiplication with ct minus 1, that is the previous cell state information. So we filter the new cell information by applying an element-wide multiplication with the input gate vector that is similar to filtering, and then we have the forget gate vector that comes into play now. So instead of just adding the filtered input information, we just perform an element-wise vector multiplication with the previous context vector. So we see, so we would like the model to mimic the forgetting notion of humans as a multiplication filter. So this was a line that was mentioned in that blog post, and you want to mimic the forgetting notions of the human as a multiplication filter. Only the important information has to be remembered. That's the importance of the role of the forget gate. So this is how the current cell state is updated. So we add the previously described term in the tanh parenthesis and we get the new cell state as shown. So now we have the output that is very simple. We have the new cell state information, just a linear combination. This is of three vectors, xt, ht minus 1, that is the previous uh, hidden state, the current time step input, and ct, that is the current cell state, the new cell state that we obtain in equation 3. So we add another nonlinear function in the end, that is a sigmoid. So we will now use the calculated cell state Ct as opposed to equations 1 and 2 where we use the previous cell state Ct minus 1. So they were used so as to because we wanted to have previous information as well and the relevance of the new information and how much of it has to be kept. So we have almost calculated the desired output, but then we'll now see the new context vector that is in the next slide. That is the last equation, that equation 4. So here we are having ht is equal to ot tan h ct. So the title in equation 4 was like we had the output, right? So that output was not like the final output. That is not the hidden state output. That was just the uh, that was almost output, not the final output. So thus one can calculate the new output like the new hidden state that will be passed on to while calculating the next time step, these gates and the cell state and the hidden state. So this new hidden state that is calculated based on this equation. So this is basically a mix of the new context vector CT with the calculated output vector OT. This is exactly the point where we claim that LSTMs model contextual information. So instead of producing an output as shown in equation 4, we further inject the vector called context. So looking back in equations 1 and 2, we can observe that previous contexts were uh, involved. You can see in equations 1 and 2, the previous contexts were involved, ht minus 1, because like wherever there is t minus 1, you know that the previous context was involved. And finally, the information based on previous time steps is involved in calculation of ht, because we calculated ot based on ct and ht minus 1 also, and ct also had information from the previous time step. So in general we are having the previous time step information involved, and that also with the application of the input gate and the forget gate. So these are actually acting as filters to the new cell information as well as to the previous cell information. How much of the information has to be kept, how much of it has to be filtered. So this entire notion of the context enabled the modeling of the temporal connections or the time related correlations in the long term sequences easy. So that is where LSTMs they uh, were able to capture the long-term dependency and they actually justified their name, long short-term memory. So now when you look at this architecture, it is a bit clear. So you see here we are having ct minus 1, ht minus 1 as the input, and then we are having xt for the current time step input, ct minus 1, ht minus 1 as the previous cell states and the hidden states, previous time steps, cell state and the hidden state, and then you are having this entire LSTM unit. And this entire LSTM unit is not as simple as it looks, because here also you are having the hidden state features that was there in the dimensions. You are not seeing that because there is this entire box, but then that is something that is important, because when you will implement it in Pytorch, you will understand the importance of the dimensions, because they are very important when you want to make these gates, right? So the uh, time steps are involved. So you see xt minus 1, xt, and xt plus 1. So here we are having the first thing as the you see two sigmoids. So one is for the input gate, one is for the forget gate. And for the input gate, after xt is passed, ct minus 1 is passed, ht minus 1 is passed, then we are having the sigmoid, and then we have the forget gate first, and then we are having the input gate second after this sigmoid. And the forget gate is applied to the ct minus 1 for calculating the ct, the first term in the calculation of ct. And the second term was the input gate into the TANH with the XT and CT HT minus 1. Okay, you will see one thing over here is that CT minus 1 is not involved because that is a peephole connection. In the calculation of the input and the forget gates, in the official Pytorch documentation, you will not find the CT minus 1. That was the third term that you saw over here. This third term in equations 1 and 2, WCCT minus 1, that is generally ignored for the easier simplicity of the calculations. So that is generally ignored, and uh, uh, in the official Pytorch documentations and in the coding part also, I'll not be using that term. So as because if without using that term because you are doing completely entire matrix multiplication, so why to increase the complexity when you are able to work without it also? Because ht minus 1 already captures the previous hidden state information and other things. So we see over here that uh, we calculate the forget gate, the input gate, and then they are combined over here through this. You can see the first row, there's this plus. So CT minus 1 into FT and IT into the tanh thing that was inside the parenthesis. That is what is being calculated over here. And then after that you get the CT, and then OT into tanh into tanh activation layer applied to the current cell state. We get the current hidden state, and that hidden state is passed on to the next layer calculations, and the current cell state is also passed. So this is now becomes easier, because earlier when you saw, it was like very overwhelming and baffling, because it was very confusing, because obviously you cannot understand this entire black box. So now we'll move on to the implementation. Okay, so I hope things were clear till now, and with the implementation things will become even more clear. I move on to the code now. So now I will move on to the custom LSTM Pytorch implementation. So to implement it on Pytorch, we will first do the proper imports. So we can see we have imported the required packages, the libraries. So before moving on further, like we have seen the LSTM equations, but just here I've changed the name of the variables. So Fn is the number of features that we have talked about, like 50 dimensional in glove embeddings. If I'm using glove embeddings 50 dimensional, then whatever is the input size that you are taking is the number of features. Then you have the number of output nodes, that is the hidden state dimension, and the batch size that has to be considered. And then after that, each W something matrix below has the shape Fn edges. Each U something matrix below has the shape edges, because it is linking a hidden state parameter to a hidden state dimensional parameter. It is what I mean through this is it is multiplying matrix multiplication is with the previous hidden state. So it is having the dimension of the hidden state only, dimension of the hidden state, and it is used to make like the input gate, the forget gate. So it is also having the dimension of the hidden state. So the matrix involved is having the dimension edges. W something is taking in input xt, and it is having the dimension feature length, and it is what it is giving out is the forget gate or the input gate. So basically it will have the dimension fn edges because of the matrix multiplication principles, as you know. So B something matrix has the shape 1 into edges, because it is basically the bias turn, and it is having the dimension of the hidden state. And it's also a learnable parameter. An XT matrix has the shape BSFN, that is the batch size into the feature length corresponding to the element index T of each sequence of the batch. An HT matrix below has the shape BS into HS because it is belonging to the hidden state at time T of each sequence of the batch. So hidden state is having dimension HS, and input is having dimension Fn, and like entire input is having this dimension as BS into Fn. But now we will see that is each time step. So now we come to the custom LSTM class that we have built. So we are creating this class by inheriting it from the RNN.module, and then also instancing its parameters and weight initializations, which we see here. And we notice that its shapes are decided by the input size and output size of the network. So you see here what it is taking as the parameter is the input size and the hidden size. So these are the hyperparameters actually. When you will declare an object of this custom LSTM class, then these are the uh, hyperparameters that you'll be passing. That is the input size and the hidden size. That is the length of the embeddings and hidden size, whatever you want to keep. And then we have uh, we we are initializing these parameters inside the init uh, function, inside the init function of the class, as we know from the OOPS concepts, that we initialize these parameters that are the self.input size, self.hidden size. These are the what you have passed while declaring the class, and now we are declaring the input gate first. So for that, we are just declaring three weights. We will do the further operations in the forward function, but in this we are declaring just the matrices, that is wi for that is of the size input sz, and hidden size input size into hidden size as we talked about it, and ui, that is of the size hidden size into hidden size because it is taking in hidden size and giving out a parameter of the dimension hidden size. This is taking in input size dimension, whereas giving out the hidden size dimension, whereas vi is taking in, it's not doing anything, it's just a bias term. So it is of the dimension hidden size because further it is contributing to the making of the input gate that is of the dimension input hidden size. Similarly, for the forget gate also we have different weight matrices because we are modeling something different as we saw in the previous slides. And this is just a parameter that we have that is learned that is a of the dimension hidden size, and it is the bias term. And similarly for CT, we also have the WC, UC, and BC. And similar for OT, we have WO, UO, and BO. And then we initialize the weights. So init weights that we are using, the weight initialization, that is the one that is using the Pytorch default NN.module. So this is how it initializes the weight from the uniform distribution minus standard deviation to standard deviation. So you can see that. So here uh, we saw one thing, that we don't have the peephole connection over here. That was the CT minus one turn in calculation of the IT, FT, and OT. But it is not there in official Pytorch documentation. That is why I didn't include it. But you can always include one more weight over here. Say self dot v F for the forget gate, and then you can do the same thing over here, and you because you're wanting to include the peephole connection, so it will have the dimension. It What is this peephole connection then? Let's understand it like that. So it is taking in CT term and it is giving out FT term. So it will also have the dimension hidden size into hidden size because CT term is also having dimension F uh, of hidden size, and this FT term is also having. So we can always include that. I'm not including it now over here, the people connection, because I'm making this in accordance with the Pytorch documentation. But since it is custom, you can always include, you can always tweak this implementation, including more weights or something more information to your cell. So you can always do that, but it's better not to complicate. So here you are having now the feed forward operation. It receives the init states parameter, that is a tuple with the htct parameters. Htct is the hidden state and the cell state parameters of the equations that we saw, and it is set to 0 if not introduced. We then perform the feed forward of the LSTM equations for each of the sequence elements, preserving the htct. So whenever it is none, the htct is initialized to 0 when it is not introduced, whereas when it is introduced, it is set as the introduced, because it's a if it is introduced, it will be in the form of a tuple of htct. Okay, like this. So now I'll not talk about that. So what this feed forward operation will receive is the input in the shape of batch size, sequence size, input size. So you know batch size, that is a hyperparameter that is set when you will create your model. So like 128, 256, or any size that you want according to your memory. Then we have sequence size and then we have input size. Sequence size is basically the number of time steps. So n, because we saw the sequence unrolling, so there is a certain number of time steps that is involved. So the number of time step is the sequence size, and one time step at a time. That is the main thing of this RNNs or LSTMs. So, and then the input size, that is the feature length that we talked about. So when you look at x dot size, so you can get the batch size and the sequence size from here. And then we have the hidden sequence that is empty now because you're passing the first time step now. So it is empty at this point of time, and it is initialized the hidden state, and the cell state is initialized to 0. And this is now it will be now uh, like further we will see how it will help in uh, predicting the next element of the sequence. So now we move towards for T in range sequence size. So sequence size means number of time steps. While every time step you pass it to the LSTM, so you have to perform these operations, right? So you declared the weights as the parameters, and now you perform these operations. What are these things that you see over here? These are exactly these equations, and you finally get the hidden state, the new hidden state. So you multiply the xt with wi, ht with ui, and then the bias term, and introduce the sigmoid for the input, and for the forget gate similar sigmoid, and then for the gt, that is the term that you use for the new cell information in the current cell state. So that was the tanh to introduce the null to make it from -1 to 1, and then there's this OT term that was the sigmoid of the uh, like the similar thing, the input and the previous cell state. And after that, you have the current cell state, how it is updated forward into CT plus IT into GT. So this is what we had studied when we were looking at the mathematics. So this input gate filters the new cell information GT, whereas the forget gate filters the previous cell information CT, and making the new cell information CT, and updating like the cell information CT, and then HT is there, that is OT into torch.tanh CT, that is the tanh layer over activation over this CT. And you know what is OT? OT is the output, and HT is the current hidden state. So we get this. So this is what we wanted. So we got the current hidden state and we got the CT, and this is what our after giving it a different shape to the hidden sequence, we return the, like this hidden sequence was an empty list, so we are appending the hidden states one by one to this sequence. So for every time step you will be appending the updated hidden sequence to hidden state to it. So in the end it will be having n elements having this I think the batch size into the output size length, and it will have n elements size. N is the sequence length, sequence size, or the number of time steps, and HTCT is returned over here. That is the final thing that we get. Let's take an example. Let's take an example of this LSTM net. For example, it is taking text sequence and classifying it into fake news or non-fake news. So you have many to one RNN or LSTM variation of the RNN. So many to one LSTM is taking n inputs, n is the sequence size, and it is outputting one thing, that is the fake, whether it is a fake news or not a fake news, and then you calculate the loss, and then you update the weights accordingly, and hence train your entire LSTM network to predict the whether the news is fake or not. So you are making a LSTM network for a text classification task. So how will you actually form the network once you have built your custom LSTM cell? Because this is important. This is what you will be using for training the model. This is not, a cell is of no use if you're not including it in your network. So you inherit it from the NN dot module, and then you have this self dot embedding thing. So say you are having some encoder vocabulary that you did, like it's encoder vocabulary. What I'm saying through this is it's a dictionary of, like, what is a dictionary size. So if you're having like 16,000, like you have a text corpus, right? So it will have a dictionary size for getting the embeddings. So that is there. And what is the dimension of each embedding that you want? So here it is 32, right? So here I've mentioned it 32. So this is the cell dot embedding. So you have this embedding for each time step. You need the embedding. Then you have the LSTM layer. So this LSTM layer is actually your custom LSTM class. I'm building it, and we are taking in here the input size and the hidden size to build this self.LSTM object. So this is a parameter of our network, and then we have this with this like information, that is 32 into 32. 32 is basically the embedding dimension, that is the feature length, and the uh, whatever and the hidden state dimension is also 32. And after that you have self.fc1, that is nn.linear 32 32. So what is it doing is it is a linear layer, that is basically a matrix multiplication to give a two-dimensional output from a 32 dimensional input. Like it is taking in the hidden state, whatever your hidden state is giving out. So hidden state output was of the hidden state dimension, that is 32, and it is giving it two dimensional output. So you want a two-dimensional output, right? When you want to classify something into whether it is fake or not fake. So this is how you build this self.fc1. So you need a fully connected layer for that purpose. So after that, you make this feed-forward network. It receives x. X was of this shape. The batch size into the sequence length. Now you are generating the embeddings to make it batch size into sequence length into the feature length. So after that, you pass it through this self LSTM, and what you finally get is hidden sequence htct. That is what your in LSTM like feed forward return, right? So it is x dash, that is a list. Okay, it is a list of all the hidden states, and here you are having HNCN, that is the last time steps hidden state and the current cell state output. You don't need these, but what you need is x dash, because that was a hidden sequence, like hidden sequence calculation that you did, and x dash is of the form, it's having the dimension batch size into the sequence length input into the output size. Output size is 32 over here because you have initialized it to 32, the hidden size, state size, but you need only the last because you have many to one. So we need the last sequence. We need the last hidden state output. So we need the output of the last sequence. That's why we've used -1, last time step output. So it is x, all the batch, all the examples in that batch, and all the dimensions of the hidden state, but only the last dimension of the sequence, that is the last time step output. So this is how you model many to one. Now obviously last dimension of the last output will have, like it is having -1, but it is -1 is the last one, but it is, since it is LSTM, it is covering the previous cell state informations as well. So it is having this x dash that you will output. So this will have the it is only in, it is considering only one dimension. So it is just 2D. You can think of it as a 2D matrix. Like if you consider all the sequences as all the, like you have sequence length n, so you have n pages, and every page is a 2D matrix of batch length into output size. So you just got the last one out, that is the batch length into output size, and since it's a LSTM, it is having the previous information as well, and you will use this to model the final output. So final fully connected layer over this last layer, last output, last time step output, and it will give x dash, and you return that x dash. That is the final prediction, and you can use it to calculate the loss now. Binary cross entropy most probably, because you have fake news or non-fake news. So x dash is over here, and you return x dash. Self.fc1 basically does is makes it into the number of labels. So here you are having to say you are having a multi-classification problem, say 10,000 labels. So this will become 10,000, and this hyperparameters that you are having, input size and hidden size, will also change for that. And uh, finally, this x dash is what you will get a prediction for from this network, and that prediction will be of a two-dimensional prediction, and you can apply like some layer over it to make it in between 0 and 1, say sigmoid, something like that. So that is what LSTM Pytorch implementation. I hope it was clear. And finally, I would like to conclude. So I like to conclude the talk. Thank you for attending, and I hope it was useful and I was able to make things, the concepts and the implementation clear. For any doubts, you can always reach out to me on LinkedIn, and these are some of the links for my LinkedIn and Kaggle IDs. So thank you again.